Okay, so what we want to do is now take entropy and try to figure out if there's a way that we can kind of use what we developed back when we talked about enthalpy and try to standardize it. So how do we set up a standard enthalpy? We measure something like this. Like we talked about the change in entropy, but we talked about in terms of formations. Okay, and so this was what the symbol looked like. Now the subscript, that F, stands for formation. Okay, and the superscript, that bubble, which indicates that the knot indicates standard state. So that means we're looking at 1 atmosphere and 298 K. Okay. So how did we set up these standard enthalpy? Remember that by definition, the enthalpy of formation, this was the energy to produce a species from the elements in standard state. Okay. Now, entropy is a different parameter than enthalpy, so we're going to have to set this up a little bit differently. So we could definitely go back to the Boltzmann equation, S equals K natural log of W, and we can define it that way, but it could get really tedious because we need to know the number of microstates, and that's harder to define, especially if we're using this for molecules or whatever. Now, there is an experimental way to determine absolute as opposed to relative entropy. We won't go into it now, but we'll rely on this fact as we proceed. Okay. Now, the standard for entropy is equal to the absolute entropy at 1 atmosphere and 25 degrees Celsius. Okay. And the reason why we want that is that this is going to give us a number that's not 0. Okay. Now, why? So we want to note the similarity to the enthalpy scale because we talked about the enthalpy of formation at 1 atmosphere and at 298 K, which is 25 degrees Celsius. So what's the difference here? There's a big difference between the two. So the difference with entropy is that it's not being compared to the elements. Okay, so we're not talking about formation. And it's also an absolute value. So you have two differences. This is not being compared to the elements, so we're not talking about formation. We're also talking about an absolute value, not a relative. Okay, so I've got a simple table here of some of the more standard molar entropies at 25 degrees Celsius. And you'll notice that as you take a look at this table really quickly, that these are all positive values. Okay. Now, some other things that we can point out. This table is divided into gases, liquids, and solids. What else can we notice? And there's a few patterns here. But if you take a look at the entropy of the gases, the entropy of the liquids, and the entropy of the solids, it seems that the entropy of the gases are going to be greater than the entropy of the liquids, and the entropy of the liquids are going to be greater than the solids. And the other thing that we can see is that the larger that S becomes, the more complex structures we'll be dealing with. So as S becomes more and greater and greater and greater, not only are we talking about phase changes, but we're also talking about more complex molecules. So that if we look at the solids here, calcium carbonate is at positive 97.1 joules per k mole. If we take a look at graphite Graphite compared to that is going to be a 5.7. So the more complex the structure, the higher the entropy. All right. Now, in the designation of the standard state formation, what letter is missing to compare to H? So again, for enthalpy, we are talking about standard states of formation. So we're missing that F. So we're missing the formation. Now, a related question, why is there no value of 0 even for the elements? Okay, and side point, if there is a 0 in the case of ions, but we're going to ignore that for right now. And here it is. If the temperature is greater than 0 degrees Celsius, okay, what that means is that you're going to have more than one possible microstate. Okay. Now, in what way are the units of the standard state different than that of enthalpy? So remember that enthalpy, we measured it in kilojoules per mole. For entropy, we're measuring this in joules per kmol. So not only is it going to be temperature dependent, but it's also going to be a smaller value. Now, earlier I said that in order to predict the spontaneity of a chemical reaction, we needed both the enthalpy and the entropy to help us determine that. Okay. Now, that being said, it can be both simpler than that, but it can also be more complicated than that. So what I'm going to do is kind of explain the two. So let's start with the simpler aspect. At this point, we can now talk about the second law of thermodynamics. And here's what the second law of thermodynamics says. The entropy of the universe increases in a spontaneous process and remains unchanged in an equilibrium process. So the entropy of the universe increases in a spontaneous process and remains unchanged in an equilibrium process. We can also write the second law of thermodynamics in an equation. Okay, and so the way that we do that, let's talk about the spontaneous first. Okay, so if we've got a spontaneous process, the entropy, the change in entropy for the universe is going to be equal to the change in entropy for the system plus the change in entropy for the surroundings. Okay, now when we add up the entropy of the system plus the change in entropy for the surroundings, this has to be all greater than 0. Okay? And for an equilibrium process, when we do the same thing, the change in entropy of the universe is going to be equal to the change in entropy of the system plus the change in entropy of the surroundings. Okay? According to what we said above, this has to be equal to 0. So, to simplify, if it's spontaneous, the change in entropy for the universe has to be greater than 0. Okay? And if a process is at equilibrium, then the change in entropy of the universe has to be equal to 0. Now, can either of these terms be negative? Sure can, yes. Can both of these be negative? No. Okay, so what can we say about the signs of the two terms if we're at equilibrium and the change in entropy for the universe is equal to 0? If that's the case, then that means that the change in entropy of the system has to be equal to the negative change in entropy of the surroundings. And vice versa. If we're looking at the change in entropy for the surroundings, that has to be equal to the negative change in entropy of the system. Okay? Just like what we saw for the first law of thermodynamics. Now, what can we say about the two? Ooh, I just wrote, sorry about that. I just wrote this part and it should have been over here. All right, so what can we say about the process if the change in entropy of the universe is negative? What that means is that we have an instantaneous process that's going to be spontaneous in reverse. So that means if we're looking at a system that's at equilibrium, it's going to go in the opposite direction. It's going to favor reactant formation. Okay. So if we were to calculate the entropy changes in a system, and we had this a generic equation, let's say you have compounds A and B, and they react to form compounds C and D. Okay. And let's say you've got stoichiometric coefficients A, B, C, and D, and these are all going to be lowercase. We could calculate the entropy of the reaction at standard state. This would be equal to the products minus reactants. So it would be the change in entropy standard state of the products minus a change in entropy standard state for the reactants. Okay, so the way we set this up, pretty much like what we set up for the enthalpy reactions back in Gen Chem I, we'll take the stoichiometric coefficient for C, and we're going to multiply that by the entropy standard state for compound C. Okay, and we're going to add up, take compound D, the stoichiometric coefficient for compound D, and we're going to multiply it by the entropy for compound D. Okay, minus, we're going to do the same thing for the reactants. So stoichiometric coefficient A times the entropy of compound A plus stoichiometric coefficient of B times the entropy of B. And so we can generalize this to form that the change in entropy standard state of the reaction is going to be equal to the sum of the coefficients times the entropies of the standard entropies of the products minus the sum of all the entropies of the reactants times its coefficients. All right, and so now we have our first problem. And what's kind of neat about this problem is that we're going to build upon this one problem as we go through the chapter, and so that as it becomes more and more complex, you get to see that build up. All right, so here's our problem. Calculate the standard entropy of reaction at 25 degrees Celsius for the decomposition of calcium carbonate. And here's your reaction. Okay, so if we look up the entropies, so we'd have to go find the standard molar entropies and look up these compounds either in this chart or in the appendix of our textbook. We would find that the entropy for calcium carbonate at solid state, that would be a positive 91.7 joules per k-mole. For calcium oxide, looking up that entropy, that standard entropy, that would be 38.1 joules per k-mole. And then for carbon dioxide, that entropy is going to be 213.6 joules per k-mole. Okay, so using our equation that the change in entropy for the reaction at standard state is going to be equal to the sum of all the entropies of the products minus the sum of the entropies of the reactants. Okay, this is going to be equal to the products, which is going to be 38.1 for calcium oxide. Okay, 38.1 joules per k-mole. This is going to be multiplied by 1, so we're good. Plus, for CO2, 213.6 joules per k-mole. Okay, that's also multiplied by 1, so we're good. Minus the entropies of the reactants, which in this case is calcium carbonate, so 91.7 joules per k-mole. Okay. That's also multiplied by 1. So if we take 38.1 plus 213.6 minus, I got 2 minus sign, so let me take that out. Okay. Minus 91.7. That will give us, that should come out to be about, if we add up the first set of brackets, that should be 251.7 joules per k-mole. Minus the reactants, which is going to be 91.7 joules per k-mole. That should give us a total of a positive 160 joules per k-mole. All right. Okay. So that's how you would do that kind of a problem. Okay, so what about taking a look at the entropy of the surroundings? All right, so what change in the surroundings occurs for an exothermic reaction? Well, we know that heat flows from the system to the surroundings. Okay, and when this happens, we increase the number of microstates. Now, how would this relate to the entropy change of the surroundings? That means the change of the entropy of the surroundings has to be greater than 0. And what change does in the surroundings occurs for an endothermic reaction? Well, the heat flows in the opposite direction. So heat flows from the surroundings to the system. And what that does is that it's going to decrease the number of microstates. Now, how would this relate to the change in entropy of the surroundings? The change in entropy of the surroundings would have to be less than 0. So we're going to see this to be a negative number. So for an exothermic reaction where we're increasing the number of microstates, heat's flowing from the system to the surroundings, that should give us a positive value. And then if the heat is flowing from the surroundings to the system, it's going to be a negative value. Okay. So what further statement can we make if the process is held at constant pressure? Okay, we can say that the change in enthalpy of the surroundings is related to the change in enthalpy of the system. Okay, and that the heat at constant pressure, the heat of the system plus the heat of the surroundings is going to be equal to 0, and that's the first law of thermodynamics. And so the heat of the enthalpy of the system plus the enthalpy of the surroundings has to be equal to 0. Okay. Now, what can we say about the temperature dependence of the entropy change? This is not a simple answer, so let's be a little bit more explicit. So, delta S is a function of temperature, which we know, joules per k-mole, and pressure. Okay, so if the temperature is high, a certain quantity of heat has less effect on the system and if temperature is low, then that means that the heat has more effect. On the system. Okay. All right, so give the resulting equation. What this allows us to do is to calculate the change in entropy of the surroundings. That's going to be equal to the negative change in enthalpy of the system divided by temperature. Okay, and so that leads us to another problem. So here's our problem now. Determine the sign of the total change in entropy and decide whether the decomposition of calcium carbonate is spontaneous under standard state conditions at 298K. All right. So we want to use this equation that we just got. Okay. We want to use that equation. In order to use that equation, we got to solve for the enthalpy. Okay, so we got to figure that out. We got to figure out what our enthalpy is. Now, we're also asking for the entropy, total entropy. And that's essentially the entropy, the total entropy of our system. The total entropy, what we're looking at is that we're pretty much looking for the entropy of the universe in this particular problem. So this is going to be the entropy of the system plus the entropy of the surroundings. Okay. Now, we do have that value because that was the value that we had in the previous problem. So we do have some of this already. Okay. So remember that in the last problem, we calculated the entropy of the reaction, and that was going to be a positive 160 joules per k mole. Oops. Okay. And so for us, this is going to be our system. That's the entropy of the system. Sorry, I've forgotten this. Okay. So we've got the entropy of the system. We need to figure out, I'm going to make some notes here. Let's figure out the enthalpy of the reaction, because once we get that, that's going to be the enthalpy of the system. Okay. So once we get that, we could solve for the entropy of the surroundings, because if we know the temperature, if we know the entropy of the system, we can get the surroundings. We know the entropy of the system. If we add those two values together, we can get the total entropy. Okay. All right, so that's our game plan. Let's solve for the enthalpy of the reaction, because that gives us the enthalpy of the system. Take that divided by the temperature, that gives us the entropy of the surroundings. We know the entropy of the system already. We add those two values together, we should get the total entropy. All right, so let's get to this. So to do step one, we got to find all of the enthalpies of formation for our compounds. So what I'm going to do, let's make a table here, delta H sub F's. So we have calcium carbonate. Okay, so calcium carbonate, that value for a solid, that value is negative 1207.6. These are all kilojoules per mole, by the way. All right. For calcium oxide, looking up these values again, this would give you a negative 634.9. And then for CO2 gas, that value is negative 393.5. Okay. So with those values, let's calculate the enthalpy of formation, the enthalpy of the reaction using those formations. So that's going to be the products minus the reactants. So you've got negative 634.9 kilojoules per mole for calcium oxide, plus negative 393.5 kilojoules per mole for CO2, minus a negative 1207.6 kilojoules per mole. Okay, so if we do everything inside the parentheses, so negative 634.9 plus a negative 393.5, and then we're going to subtract a negative 1207.6, which is the same as adding. That should give us a positive 179.2 kilojoules per mole. So based on what we're told in this based on what the number's telling us, we know that this process is going to be endothermic. Okay. All right. So now that we've got that value, now that we've got the enthalpy of reaction, we can use that. This is going to be our enthalpy of the system. We can solve for the entropy of the surroundings. And that's going to be equal to our value of that's going to be equal to negative change in enthalpy of the system divided by the temperature. So for us, that's going to be a negative. That value was negative 179.2 kilojoules per mole divided by the temperature, which is 298 K. If you divide those together, that's going to give you a negative 0.601 kilojoules per K mole. Now, keep in mind, we got to keep the system, keep the units right. We're in kilojoules. Entropies are reported using joules, so we got to convert this to joules. So that should give us a negative 601 joules per K mole. All right. So that is our entropy of surroundings. Now, what we need to do is calculate the total the change in the total entropy. That's going to be equal to the change in entropy for the system, which we calculated before, plus the change in entropy for the surroundings. Now, the surroundings is the value that we just calculated, the negative 601 joules per K mole. The change in entropy of the system, that was the number that we calculated the first time in our first problem, where we have where the total entropy of that reaction was positive 160. So 160 joules per K mole times the change in entropy of the surroundings, so plus a negative 601 joules per K mole. So positive 160 minus 601, that's going to give you about 441.3 joules per K mole. And this is a negative value. So what this tells us, that negative sign tells us that this is not spontaneous. So to answer the question, determine the sign of the total entropy, which we know is negative, to decide if this is going to be spontaneous. So based on what we're telling you, because the sign was negative, we know that this is going to be not spontaneous. If it was positive, then we would know, yes, it is spontaneous. All right, so we know a lot from the change in entropy, but what will this not tell you? It's not going to tell you how fast the reaction goes. All right, now we talked about the second law of thermodynamics. We're ready to talk about the third law. And the third law of thermodynamics says this: the entropy of a perfect crystalline substance is 0 at 0 K. Okay? So the entropy of a perfect crystalline substance is going to be 0 at 0 degrees Kelvin. If we were going to use this in an equation, if we go back to the Boltzmann equation, entropy is equal to the Boltzmann's distribution constant times the natural log of W, where W is the where W is the number of microstates. If this is equal to 0, if the entropy is 0, okay, and then we have this equation, K times natural log of W. In order for this all to be 0, W has to be equal to 1. So what that tells us is that there's only one possible microstate for the system. All right, now, what warnings must be given regarding this value of absolute entropy? Now, this only works if it's pure, and only if it's a pure crystal. Now, what is the great advantage of this standard state function? There's actually two. It's absolute, so not relative. Okay. And so what that means is that we can determine the change in entropy at all temperatures. All right. Now, before we take a look at another thermodynamic term, let's take a look at this figure. All right, so what we're looking at on the y-axis, we've got entropy. On the x-axis, we're looking at temperature in Kelvin, and we're noticing that as the temperature is increasing, the entropy increases until we get to our melting point. We're going to see that entropy jump up, and it's going to be pretty vertical. And then once we get to a full liquid state, the entropy is going to increase gradually. And then once we get to the boiling point, again, we go completely vertical. So what we're seeing is that there's a couple things that we see in this figure. That's the change in entropy going from solid to liquid is going to be less than the entropy going from liquid to gas. Okay. All right. Now, we also see that every time we look at these increases, so if we compare the increase of the liquid to the increase of the solid, there is an increase in temperature, okay, but the graphs, the curves are not linear. So they're not going up at the same amount each time.